Hey, welcome back. It is now day 4, right? On our ongoing quest to learn the 10 different tests for convergence and divergence of series. We're now in section 9.5 of your textbook. Sorry, that's an old textbook that I used to use, 9.5. And I have assigned some MyMathLab problems just for practice, labeled day 4. And today we're going to cover two more tests, the direct comparison test and the limit comparison test. The direct comparison test is really pretty interesting. If you have two tests, or two series now that we're comparing, A sub n and B sub n, and it's always that A sub n is less than B sub n. Okay, so you've got 0 is less than A sub n is less than B sub n. If B sub n converges, then A sub n is also going to converge. Okay, so think about it. You've got 0 here, you got A sub n, and you got B sub n. If this converges, well, this means this has like a stop sign here, right? It's going to stop. We'll pretend that's an octagon there. It's going to stop, then A sub n is also going to have to stop. It's going to have to converge. Conversely, if A sub n, so we'll draw another example over here. You got 0, A sub n, and B sub n. If A sub n diverges, in other words, that keeps going, it doesn't have an end, then isn't that going to push out B sub n, and it will also have to diverge? The interesting thing with these is now we can compare some more interesting, I guess you would say, series to one of the series that we should already know about. And I would kind of think of this as like the parent function. Simplify this expression right here. What would you like to compare that to? Well, I'm going to say we compare this. And you don't want to oversimplify it so that it doesn't make any sense at all. But this series here, I would say, would seem to make sense. The series from n equals 1 to infinity of 1 over n to the third. Given your recognition of that we did just, gosh, was it yesterday? The P series, which, what? Converges by the P series. So we have to reference the test that we're using on the compared to, okay? So that converges. We need to make an inequality because we need to make sure that it's the right way. If 1 over n to the third is one of our terms, and 1 over n to the third plus 1, well, which is that? Think about it. If you're dividing by a slightly bigger denominator, isn't the inequality going to go that way? Yeah, so this one converges, therefore this one. And we're going to say for all n, because that's true. There aren't any restrictions as n is greater than 7 or whatever. So for all n, this would be true. Slightly bigger denominator, it's going to be divided by a bigger denominator. This fraction is going to be smaller. So then we could say, therefore, this series, and when we say series, we're talking about the original. I'll write it out this time, but you wouldn't have to. Series 1 to infinity of n to the third plus 1 is going to converge as well by direct comparison test. I will tell you, in your textbook, it calls it the comparison test. So I'm going to call it direct comparison test just so it doesn't get confused on the other tests that we're going to talk about next. Okay? Think about it. We're comparing one that we should know about, so you're going to have to think about the one that you're comparing it to one that's kind of similar to that. But if this converges and it's similar enough, then that one's going to, in this case, converge because the inequality works that way. Okay? Well, what would you like to compare this one to? That's, for some of us, is going to be the challenge. We're going to compare that to the sum from n equals 1 to infinity of what? Well, if you think about it, 1 over 3 to the n is your business part of that. Plus 2 really isn't changing it that much, is it? So we're going to compare that. to 1 over 3 to the n. This is not a p-series test. Be careful. I'm going to rewrite this if you're not seeing what I'm seeing. N equals 1 to infinity. What if I make this whole fraction, 1 over 3, all of that to the nth power? What kind of series is that? I'm hoping you're thinking it's geometric, because that would be correct. You're multiplying to get from term to term to term. You have a repeated r, that common ratio. If you've got something to the same power n, you can see that this is geometric. Okay, so which is going to do what then? Well, if r is less than 1, we're going to say that converges. Converges by geometric series. So we have to name why the compared to series converges. And if you want, you could say 1/3 is less than 1. Okay, that's true. Okay, we need to set up an inequality. So I'm comparing 1 over 3 to the n. And I'm going to write an inequality here. I'll put the inequality sign in the middle here in a second. 1 over 3 to the n plus 1, 3 to the n plus 2, right? Just the original one that we had. Well, again, since 1 over 3 to the n is common in those two, we're adding a little bit more. For all the values of n, wouldn't this be a slightly bigger denominator? If we're divided by a bigger denominator, it is indeed less than. So even though I wrote it in opposite order just to have you think a little bit, it's still the same case, right? Where the one that we're comparing it to is trapped by the one that we're comparing it to. The one that we want, our original series is trapped, is going to, so if this one's converging, this is less than it, it also has to converge. Therefore, series, and again, when we say series, we're talking about the original one, the series converges by direct comparison test. Any questions on that? Please shoot me a message here. Comparison. Okay, well, let's look at another one. I'm going to compare this to 1 over square root of n. Here to the sum n equals 1 to infinity, 1 over square root of n. Maybe you're not seeing that. I'm going to say that's equal to n equals 1 to infinity of 1 over n to the 1/2 power. Isn't that a p-series? In fact, isn't that a divergent p-series? Because p is less than 1, that 1/2 power there, which diverges by p-series test. So we need to set up an inequality. Well, I've got 1 over square root of n, and I've got 1 over square root of n minus 1. I'm going to say this is less than, but if you're not sure, let's cross multiply that, right? Because wouldn't that be true? If we cross multiply, we'd say, okay, well, square root of n minus 1 is going to be less than the square root of n. Isn't that true? So since we're subtracting, this denominator is actually going to be a little bit smaller. The denominator is smaller, that means this fraction is going to be greater. Okay? And that would be true for all n. Greater than, let's see, 1. And here we've got the beginning at 4. So they've taken care of that issue dividing by, right? If it was 1, it'd be 0, so that would work. So we're going to say for 4, for n greater than 4. So then it definitely fits our condition there, for n greater than 4. Therefore, in this case, this is diverging. It's less than the one that we want, so it's going to be the second case where if the one that's less than diverges, then the one that we want is also going to be pushed out and it's going to diverge as well. Series diverges. You have to check that inequality because there could be cases where if one converges and the other one, if the inequality isn't the right way, we need to check that first. Okay, you need another test, basically. Converges, or no, sorry. Therefore, the original series diverges by direct comparison. All right. This next one is similar because it's got the word comparison, but we're now comparing limits. Okay? So again, we still have two a sub n and b sub n, and we're going to have to think about finding what the other compared to series is here. But here we're saying this: if the limit as n approaches infinity of a sub n over b sub n, the one we want and the one we're comparing it to, is equal to some finite L, some limit where it's both positive and finite. Okay, so it needs to be some number L. It could be a fraction, so we'll see. I'll give you an example where it doesn't matter the order that you divide those by, the numerator or the denominator. But if it's both positive and finite, then they're going to act the same way. If you can find where some limit of some ratio there is finite and positive, then the series a sub n and b sub n are both going to either converge or both diverge. So you're comparing it to something. Now, with this one, I would say if we compare it to what? Compare it to what? I'm trying to get a finite limit. In fact, I'm, in other words, trying to think about taking a limit as n approaches infinity. What would cancel out all of the terms and just leave the leading coefficients? Aha, you can kind of see it. I'm going to compare this to 1 over n squared. 1 over n squared. Okay? Not n squared. That would, I mean, yeah, but you'll see. 1 over n squared is going to be the one that we compare it to. Compare to the sum n equals 1 to infinity, 1 over n squared, which is going to what? State what that is right away. 1 over n squared, isn't that p-series converging? Converging p-series. Okay, so I'm going to set up a ratio now. The limit as n approaches infinity of 1 over n squared over 1 over 3n squared minus 4n plus 5. Okay, wow, that looks like a big mess, but if we flip and multiply our denominator, we'd get the limit as n approaches infinity, 3n squared minus 4n plus 5. Over n squared. Flip and multiply. Okay? Now, got to make a note here. It does not really matter which one of these you put on the top. Because if we had 1 over 3n squared, that term on the top divided by 1 over n squared, so basically the reciprocal of this big, ugly, giant fraction here, you'd end up with the reciprocal of that. So you'd have n squared over 3n squared minus 4. Take that limit. Well, if we take this limit now, the exponents are the same, right? So we've got leading terms, and we'd put a 1 there if you don't see the leading term there. That's going to be 3. If you did it the other way and had it the reciprocal, wouldn't you get 1/3? My question to you, aren't those both finite and positive? 3 or 1/3 are both finite. I can point to the number 1/3 on the number line without any doubt. It's positive. 3 and 1/3 are both positive. Therefore, they're going to act the same. Okay, so we have some finite limit L. So then we're going to say, therefore, the series converges. Since the compared to series converges, this one is going to act the same way. That's a converging p-series. This new series that I've got is going to converge by limit comparison. Not direct comparison. We're not doing an inequality. We're taking the ratio of the limits, okay, by limit comparison. Okay, this next one, what would it take to get these to match in degree? Well, I'm going to compare this to the sum n equals 1 to infinity of, what do I need? An extra n to the 4th, make that n to the 5th. Well, if I divide by that, it will be 1 over n, which is what? Well, if you're thinking the word harmonic, I like that. It is harmonic. What else is it? Diverges. Yes, harmonic series diverges. So let's take our ratio of the limits now. The limit as n approaches infinity. Wow, this is a big mess. N to the 4th plus 10 over 4n to the 5th minus n to the 3rd plus 7 over 1 over n. See how I did it, the compared to on the bottom? Because again, doesn't matter as long as we get a, well, if we flip and multiply, that would bring an n on the top, right? So I've got the limit as n approaches infinity, n to the fifth plus 10n over 4n to the fifth minus n to the third plus 7. Take that limit, the exponents are the same, that's 1/4. So therefore, we're going to say that the series what? Well, since that compared to series 1 over n diverges, our original series, that hot mess right there, is also going to diverges by limit comparison. Okay, how we doing? 1 over n to the third, what would you compare that to? I bet you're getting the hang now. I'm going to compare that to the sum n equals 1 to infinity of 1 over n to the third. Now, a good question that you might be thinking, are there other tests that we could use? Yes, I'm using the limit comparison now. Couldn't I use the direct comparison maybe? Maybe, but yeah, so think about what, I mean, that's part of the skill, the practice. That's why I'm giving you some problems to practice. I would use limit comparison on this one because it would be easy to compare and match that up and just take the limit as n approaches infinity. What is that? 1 over n to the third. P series, right? But what is it? Converging or diverging? Well, p is greater than 1. So it's going to be a converging p series. Take the limit then of the ratio of those two series. The limit as n approaches infinity. 1 over n to the third minus 2 over 1 to the n to the third. Flip and multiply. Limit as n approaches infinity. N to the third over n to the third minus 2. Exponents are the same. We've got our leading terms. Coefficients, that limit is 1. So n to the third divided by n to the third minus 2. That minus 2 is inconsequential. We've got our limit. Since our compared to function is converging, therefore we're going to say the series converges by limit comparison. All right, last example. 1 over square root expression. Well, haven't I been getting the exponents or the degrees to match? What if I try this then? 1 to infinity of 1 over square root of n, or 1 over n to the 1/2 power. Isn't that a p series? Which is a diverging p series. So I'm going to take the limit as n approaches infinity of 1 over square root of n over 1 over square root of 3n minus 2, and recombine those terms here. It's going to be the limit of square root of 3n minus 2 over square root of n. Here's an idea. If you're not really liking that whole square root or square root of, what if I did this? The limit as n approaches infinity of some mega square root here. I can bring those all under 1. Take that limit, right? Because, oops, this is not an n, sorry. There it is. That's an n. So 3n minus 2 over n. I'm just combining those separate radicals into one radical. Take that limit. Well, the exponents are still the same. The degree is the same. N to the 1, n to the 1. So we would have 3, but we've got, wait, we've got the square root of 3. So that's the square root of 3. Is that finite? Yeah, it's the square root of 3. Okay. Didn't say it was rational necessarily, but it is finite. There's 1 square root of 3. And is it positive? Sure. Okay. So since our compared to series diverges, we're going to say therefore this series diverges. They're going to act the same. Diverges by limit comparison. Okay, that was test number 7. We're 3 more to go. The next topic we'll be doing the next time is called alternating series, and there's a lot of applications for that too. So stay tuned, do a little bit of practice, and again, as always, I'm hoping everybody's well. Get some fresh air, get some exercise, but hopefully you're getting some math in here too as we get you prepared for whatever your next steps with calculus might be. Hang in there, and I will talk to you next time. Have a good one.